let's take the graphs of trig functions and use them in practical applications. So here we go. One of the things that we learned in a previous lesson was this. Now this works whether it's sine or cosine, but the absolute value of A is the amplitude, and then the period is determined by B. The period is not B, it's determined by B, so 2 pi if you're in radians over B. And then the vertical shift is D. And then in this one, you're also going to see a horizontal shift, in this case of 2014. But we're not going to worry about the horizontal shift too much within this context. Here we go. Astronomers have noticed that the number of visible sunspots varies from a minimum of about 10 to a maximum of about 110 per year. Just stop right there and let's go ahead and start interpreting what we're looking at and what we're reading. This is going to be the graph of how many sunspots there are in a given year, and the minimum is 10 and the maximum is 110, which is consistent with what we've already read. Okay, further, this variation is sinusoidal, repeating over an 11-year period. That word sounds familiar within the context of what we're doing. The last maximum occurred in 2014, as of the recording of this video, which is 2024. And the cosine function and graph below model this phenomenon in terms of time t, which represents the year. This function is in radians, not degrees, which I would like to think is going to be fairly obvious from this 2 pi here. Plus, we're adults now, we use radians. So, let's go for the easy thing first. How many sunspots can be expected this year? All we really need to do is just find f of the current year, which of course, as I said, I'm recording this in 2024. So we'll plug in 2024, and I'm just going to crank that out. Now my calculator is in radians, and yours should be as well. So 2 pi over 11, and then 2024 minus 2014, because it's t minus 2014. So let's just put a 10 right there, and then close out all those parentheses, and then add 60. Wonder what that plus 60 does. There we go, 102. So this year, we would expect 102 sunspots. Spots on the sun, astronomers notice them. They take binoculars and stare at the sun for hours on end. It's really healthy for their eyes. So, I'm kidding, don't try that. So we're kind of in 2024, on the up end of it. Now 2025 will be 11 years after that, and just because it's worth doing, check this out. In 2025, we'd have 2025 here, 2014 here. Subtract those, you'd get 11. I predict that this answer will be 110. What? Okay, that's the maximum. It's going to do that. Just saying. Okay, using correct units to interpret the period, amplitude, and midline of this function. I'm going to use complete sentences for this because complete sentences are good things to use, so we can articulate our thoughts and do them well. Okay, the midline is the last thing they asked about, but I think we can look at this and say, oh my goodness, there's a midline. Now that's not enough of an answer. Let's articulate it. And the midline is 60. So this is 60. So when we were graphing these by hand, we would say, oh, there's the midline right there. It's at 60. And from the midline, we would go up or down the same amount. How much? That's going to be 50. 50. And this is truly the amplitude. If this was negative 50, I'd be reluctant to point out and be like, hey, look at the amplitude. But this is really the amplitude, because you never can have a negative amplitude, but that's not negative. Now, the period is not 2 pi over 11. We'll talk about that in a minute. So here goes. Let's start articulating our thoughts. The amplitude is 50. What does that mean? Which means that the number of sunspots can be as much as 50 more or as little as 50 less than 60. 60, where'd that come from? That's your midline. This is your vertical shift. If you graphed it by hand, we'd call it a vertical shift. So our vertical shift 60, just shift this thing up 60, and then I'd be like, oh, well, let's go 50 above, 50 below. Less than 60, which is the midline. Okay, we've talked about midline, we've talked about amplitude, we haven't talked about period, and let's figure out what the period of this thing is, and once I crank out the answer, it's going to make so much sense. So, again, back to an old equation from a previous situation. If we had this with lots of random letters in there, it seems, B is not the period, but B determines the period. And just for the sake of explanation, I feel like writing that again. So sine or cosine, BX, and then plus D. And I know I'm leaving off the letter C, and the letter C actually is the horizontal shift that happens here, not relevant to what we're dealing with in the specific way they asked the question. But B is going to help me determine the period. So the period is a full circle, radians in this case, over B. So let's keep going with this idea. So the period is 2 pi over B. Well, B is this guy right here. This is B. 2 pi over 11. So 2 pi over 2 pi over 11. Now it gets sloppy, and you might be tempted to mark out your 2 pi and your 2 pi, and you would not be wrong to do so. But I don't want to do too much and overlook what's happening here. We really have 2 pi divided by 2 pi over 11. If I mark them out now, I might be tempted to skip steps that I would not be explaining well enough. So 2 pi over 1, because, yeah, multiplied by 11 over 2 pi. And we can cancel these, and we are left with 11. I knew that from the very beginning because it repeats over an 11-year period. Period. So they told you the period and used that word in there. The period is 11 years, and I would like to articulate that. So just to articulate a little bit further, the period is 11 years, so each complete sunspot cycle lasts 11 years. There we go.